Okay, so review of work energy theorem. Back up one here. Okay, so remember that with work energy theorem, okay, that work is a change in energy. Specifically, it's mechanical energy, but as we said in Science 10, we're only ever going to have problems where either potential energy or kinetic energy is changing. Okay, so the first challenge of the question is to write down the givens, and from the givens, figure out, is it kinetic energy that's changing or potential energy? Okay, so how do I know if it's kinetic energy that's changing in the question?
It will include speed or velocity.
Right, there'll be some sort of change in speed or velocity involved in the question. So something's being pushed from rest to a certain speed, or it's being slowed from a certain speed to a certain speed. Okay? In any case, there will be an acceleration happening, and you won't be able to solve it using an acceleration problem or acceleration formula. It'll give you force or distance or some other thing like that. Okay? So if there's a change in speed, kinetic energy is changing. How do I know if there's a change in potential energy? There'll be a change in height, right? Something will be lifted or carried, okay, or something like that, and there'll be no change in velocity, just a change in height. All right, so that's what we have to look for. That's what tells us whether it's potential or kinetic energy that's changing. Okay, once we have determined what type of energy is changing, we may or may not have to use the force times distance. Okay, but we will likely have to use the final minus the initial part. That's what delta means. So if it was kinetic, it's final kinetic minus initial kinetic, final potential minus initial potential. Okay? And if we're not told what the work is, or not being asked to find just the work, okay, then we'll have to put the force times distance over on this side. And then we simply put in the formulas for whatever type of energy is changing. Okay? So we could have this, force times distance equals m times g times h final minus m times g times h initial if it's potential, or we could have this, final kinetic minus initial kinetic, and then from there it's algebra. Okay, so it depends on what you're being asked to find, what you solve for. Those steps are always the same for a work energy theorem question. Okay? And those are arguably the tougher steps. The other stuff, like I said, is just algebra. It's just a matter of being able to isolate a variable. Okay? And oftentimes, okay, if we're having to solve for like a height, okay, or something like that, one of these energies will be zero, like it starts from the ground. Okay? If the question is a potential energy question that starts on the ground, what's my initial potential energy? Zero. Okay? If we start on the ground, HI would be 0, and anything multiplied by 0 is 0. Okay? And then similarly, if I had a kinetic energy question and it said it started from rest, or came to rest, or stopped, okay, then one or the other of these would be 0. Okay? If it started from rest, the initial would be 0. If it stopped, then the final would be 0. Okay? Everyone follow me there? Right, so like I say, it's just a matter of seeing lots of different examples so you can see what's the same about every question, but also what's different about every question. Okay. So, let's have you guys try this one, because I don't think that's not the right answer, because I changed something in the question. So that is no longer the correct answer. I will figure out the correct answer while you are working on this question, okay, and then we'll go through it together. So get it copied down and get started on it, okay? Same pattern as always. Givens. Work is a change in what kind of energy? Set it up, do the algebra. Okay, so I just did it and it worked out to be an unreasonable number. So I'm going to change this down to 0.6 meters. That will give a more reasonable number. Okay, so the context of this question is a pitcher throwing a ball. Okay, we're told as far as givens go, we're told the mass of the ball, 0.250 kilograms. We are told the force the pitcher exerts on the ball, 300 newtons. Okay, and we're told the distance over which they exert that force, 0.6 meters. Okay, we're looking for the speed he will release the ball. Would that be the initial or the final speed?
Initial.
It would be our final, because, I mean, this is where you have to get stuff from the context of a question. This is why we do so many examples, because this part is tricky. This is I read the question and I visualized the situation, okay? Visualize somebody at a baseball game standing on the pitcher's mound, and they've got the ball in their glove, and they're watching the catcher for the signals. How fast is the ball moving? Right? Initially, the ball is moving at 0 meters per second because he hasn't done anything to it yet. It's after he's exerted the 300 newtons of force over that 0.6 meter distance of the windup, okay, that he imparts the velocity to it. So we're actually, from the context of the question, not directly, but from the context, told that VI is 0 meters per second and VF is what we're looking for. That is, in my opinion, and I've been doing this physics stuff longer than you've been alive, that is the trickiest part of almost all physics questions. Because it's like reading comp, which I don't know about you, I find that tricky. Okay, like when we did an exercise where they were showing us how they teach and evaluate reading comp, while the English teachers were doing that one day, we're like, deer in headlights. Okay? We wrote down what we thought the thing was about, and they're like, no, that's wrong. We're like, oh, okay. Because it's hard sometimes to get what you need from a written paragraph. Okay? And that just takes practice. Okay? All right, so now that we've done that visualization and we've figured out what's in the question, now we want to move to work energy theorem, because we know work's being done. There's a force and a distance in here. Okay? And we know that the kinetic energy is changing because there's no mention of height, and they're asking us about speed. Is that a fair conclusion to arrive at for that question? Okay. So then, okay, we're going to expand this out, and we're going to say force times distance equals our final kinetic energy minus our initial kinetic energy. Okay, now if you didn't get this far, make sure you're writing this down as I go through it. Okay? All right, so now that I've got this written down, can I expand this out further? Okay, what's the formula for kinetic energy? Christian?
Half of mass times speed squared.
Right, 1/2 mv squared. All right, so I got force times distance equals 1/2 times the mass times, in this case, the final speed squared, minus the initial. But do I even need to write that? I don't, because it's what number? It's 0. Okay, we said initially the ball wasn't moving, so thus it had no initial kinetic energy. So there we are. Now we're to the algebra. Okay, that's the part that's patterned. Okay, what's different every time is what you solve for. Okay, but this part is the patterned part that's the same for all work energy theorem questions. Okay, so I'm supposed to solve for VF. So to do that, I would do some algebra. I'd divide both sides by half of m so that it cancels. Half of m comes over here. Okay, and then I'm going to square root that to get VF. Okay, so when I plug in my numbers, I'm going to have 300 newtons times 0.6 meters, so my force and my distance, divided by 1/2 times the mass, which was 0.250 kilograms. Okay, and when we do that, we should get 37.9 meters per second. In your calculator, sorry, I forgot to fire that up. In your calculator, there's a couple of ways to do this. Okay, there's the do it all in one step with lots of brackets way, and then there's the do it piecemeal. Okay, so if I wanted to do this question all in one step with tons of brackets, I wouldn't recommend it. I basically never do it this way. Okay, I'd have 2 sets of brackets, and then I would have 300 times 0.6, and then I would close that and divide it by another set of brackets, which would be the 0.5 times 0.250. Okay, then close that, close the full set. All right, I got 37.9. Okay, so you can do it that way, but I find people mess up the brackets, forget something. Okay, the big thing here is that doing it this way and doing it piecemeal, you have to make sure that you separate the top operation from the bottom operation. You can't just punch this in like this. Did I get the same answer? No, because it went from right to left, which is not the same thing as dividing the top by the bottom. Okay, so if you've got something on the top and something on the bottom, enclose the top, enclose the bottom, or do those operations separately. The way I would do this myself, I would go 300 times 0.6, hit enter, and then I would go 0.5 times 0.25, hit enter, and then I would go, all right, now I'm going to take those two numbers, and I'm cheating because I can do this on my calculator, not everybody can. Whoop. Okay, it's top divided by bottom. Okay, that's what I find to be the most common mistake that people make if they're getting 4 out of 5 or 5 out of 6. They've got all the work and it's all right, and then they didn't enter it in the calculator correctly. Okay? All right, questions on that one? Did that follow the same pattern as all the ones we did on Wednesday? It did. Okay, that's the thing. We just got to learn that pattern, okay, so we can figure it out. Okay, write this one down and give it a try. It's very similar, okay, at least the first part of it is. Okay, let's go over this one. So if you didn't get it done, just follow along and listen carefully here, okay? So first thing I want to do before I even get to the givens is, again, I want to visualize this situation. So I've got a car driving down the road at 20 meters per second and it slams on the brakes. What does that look like when a car slams on its brakes?
It shifts forward.
Yeah, the nose of the car goes down, the tires squeal, okay, and there's like, smoke sometimes comes out from the tires, okay. What does the sound and that smoke and all of that represent? Lost energy. Okay, that means the energy of the car is changing. Okay, that's what those things we see and hear, the sound, the smoke, all of that. That is mechanical energy being lost, okay, being converted into other forms of energy that are going out into the surroundings. So if there's a change in the mechanical energy of the car, is work being done? Okay, so we know this is a situation where work is being done. Okay, and we can say, all right, work's being done. What kind of energy is changing about the car? Well, it looks like it in this question well, it goes from 20 meters per second to 6 meters per second. Its speed's changing. So what kind of energy is changing? It's kinetic energy. All right, now I can write down my givens. I have a force, a braking force of 10,000 newtons. Okay, and I've got an initial speed of 20 meters per second, a final speed of 6 meters per second, okay, and a mass of 1,700 kilograms. And I'm trying to find how far the car will travel while it's slowing down. Okay, everybody with me so far? Okay. So when I start setting up the next part here, the next part of the pattern, that's the same for every question, okay, I'm going to go force times distance. I know I have to do that because I'm looking for distance and I was told the force, so I'm going to need those items. Okay? And then I'm going to put in the change in kinetic energy. Remember that change means the final kinetic energy minus the initial kinetic energy. Okay? Do I have formulas that will calculate those energies for me? I do. Okay, so next I want to plug those in. Okay, at this point, as I was walking around, I saw a few people punching stuff into their calculators, and when they did this part of the operation, that subtraction, they didn't like the answer they got. What felt wrong about it?
It was
It was negative. Is that okay? Did the car gain or lose energy as a result of this work? It lost it. So it should come out negative. Okay? But then people are like, but then my distance comes out negative. And that's where I haven't taught you this, so it's okay for you to be confused on that. If I'm going to slow down, which way is the force pushing the car?
The other way.
The other way. This number's also actually negative. Okay? I didn't tell you that because you were looking for distance, which is a scalar quantity anyway, so it didn't matter whether it came out positive or negative. It was going to be no sign anyway. Okay? But in the truest sense, force is a vector quantity, and your brakes exert a force backwards. Okay? So when I go to manipulate this to find distance, I need to move the force over to the other side, like so. And I saw lots of people got to that step. Okay, and that was good. Now I want to plug in my numbers. So when I do this, I'm going to have 1/2 times 1700 times 6 times 6 squared minus 1/2 times 1700 times 20 squared. And then I'm going to divide that by 10,000 newtons. Okay? And if you did that, and you got a negative number for the distance, that was fine. That's okay. It was distance. Distance is scalar. We don't put a direction on it anyway. Okay? But in the truest sense, the right way to do this, and the way we would do it in Physics 20, is because we'll have done all kinds of vector stuff already, we would recognize that force is backwards and thus negative. For this course, I'm not worried about that. You're still going to mathematically get the right answer. Okay? All right. So when we punch all of that in to our calculator, this is how I would do it. Okay? I would go 0.5 times 1700 times 6 squared, get my number, minus 0.5 times 1700 times 20 squared. There's my negative number, the one that people didn't like. Okay? Divided by negative 10,000, or if you did just divide it by 10,000, you got negative 30.94. And that's fine. Okay? It was distance. We don't put a direction on distance, so you just wrote 30.9. Okay? Everybody all right with that? Okay. Was there very much algebra in that question? What was difficult about that question? Because it was a tricky question. So I'm not trying to be facetious here. What was tricky about that question? Figuring out why things happened the way they did. Okay? And that's why before I start writing anything down, I talk about visualizing the question. I talk about, it's telling me a story, I need to see the story in my head. Okay? Most physics problems are telling you a story. I won't promise that they're exciting stories, okay? But they're always stories, and you have to get what you need out of them. Okay. Let's try this one, and then we'll take a little break after this one. All right, so we got a slingshot aimed straight upwards and drawn back 0.4 meters with a force of 1,500 newtons. Okay, the rock is going to reach a height of 30 meters. I want you to find the mass of the rock. Where do we assume the slingshot is being fired from?
Earth.
Yeah, on the ground, like the person is literally laying on the ground. Okay, so what's the initial height?
0.
Okay. All right, so something I often see on this question is people confusing the height and the distance. Okay, and that's just, again, it's a matter of experience and reading the context of the question. The distance always goes with the force. Okay, the distance is how far you exert the force over. So think about a slingshot. Okay, what is more reasonable for the distance I stretch the rubber band in a slingshot? 0.4 meters or 30? 0.4. I've never seen a slingshot that can be stretched 30 meters. Okay, plus in this question, it makes it a little bit easier because it says the final height is 30 meters. It says it reaches a height of 30 meters. Okay, so we know that that's a height. So we shouldn't get too confused over that, but it is something that I see. Okay, it's just a matter of getting the hang of reading the context of a question. So, I know it's shot straight upward. There's no mention anywhere in here about speed. So this is a change in potential energy. So we know that in this particular problem, the work is changing the potential energy. Okay, we know the initial height from the context of the question to be 0 meters, because you're usually standing on the ground when you fire a slingshot. Okay, I've never seen somebody flying through the air fire a slingshot. And not that I'm saying it can't happen, but I'm sure in this question that's not what's happening. Okay, we know our final height is 30 meters. We know the distance is 0.4 meters. And we know the force is 1,500 newtons. All right, we're looking for the mass of the rock. Okay, I'm going to expand this out now. Right? I know that I have force and distance, so I'm going to expand work to its formula. And then I'm going to expand this to its formulas. Okay? That's going to be m times g times h final minus m times g times h initial, because that's what this means, right? It means final potential minus initial potential. Now, because of the context of the question, what do we know the initial potential energy to be? 0, because it's on the ground where you cannot fall any further. Okay, so we can cross that right off, which is handy, because otherwise there'd have been 2 m's, and that would have been trickier. Okay, now there's only 1 m to solve for, so that saves us a lot of bother. All right, I need to isolate m. So what do I do with g and hf? Divide them over, right? That will leave m isolated on the other side. Right? Now I just plug in my numbers. 1,500 newtons times 0.4 meters divided by 9.81 times 30 meters. Okay, and again, I got to make sure my calculator does what I want it to do. Okay, and that will be that it separates the top from the bottom. Okay, so I'm getting 2 kilograms, which is still a big rock. But that's all right. That's just the way it worked out. Okay, that's a 5-pound rock. I wouldn't want to get hit by that. It's a lot. Okay. All right. Is that making a bit of sense still? Okay. So did that still follow the pattern? Okay. It's really important that we get that pattern down. This part here is the most important part. And when it comes down to me marking something on a test or a quiz or something like that, that's a mark. That's a mark. That's a mark. The manipulation is a mark. The plugging in of numbers is a mark. Okay? The answer is a mark. 5 or 6 marks. And you don't have to get the right answer to get 4 of them. Okay? You just have to be able to read the question and get what kind of energy is changing and set up the pattern. Okay? That's 4 out of 6 or 4 out of 5 marks. Okay? That part everybody should be able to do pretty well. Okay, sorry, that took a little longer than I thought, but I'll give you the last 4 minutes off. Went pretty hard today. Okay?